Thank you for having me. We have rewritten Iceoryx2 in Rust, and this is something which I want to present today here. And first of all, allow me to introduce myself. My name is Christian Elczyk. On GitHub, I'm also known as Elfenpiff. I'm one of the core maintainers of Eclipse Iceoryx. I was also already a maintainer at Bosch times when it was not called Iceoryx, and also guided away from Iceoryx to becoming an open source project, and now I'm here in the 7th year. And this year, with a friend of mine, we created a company called Excite.io, GmbH, because we wanted to really have a company behind Iceoryx, which really pursues the further development of Iceoryx innovation. And this is something which in our past we could not do as we wanted. And now we want to really have an open core business model, drive innovation, and then support other peoples with Iceoryx and the ecosystem. So this is our table of contents. We want to talk about this. First of all, what actually Iceoryx is, what problems it solves. There will be a lot of, let's say, complicated words, so therefore we go one by one through the technical details, explain them in detail, why we require this, why we require exactly this library, why we choose Rust, and why you should use Iceoryx if you have the fitting use case. And also our grand vision, which overlaps a little bit with U protocol. So, first of all, what is Iceoryx? Iceoryx is a true zero-copy communication framework. It currently is in the second iteration, or in the next generation. One of the biggest critiques of Iceoryx1 it was that it was centralized, meaning you required a central daemon, a broker, we called it RouDi, to establish communication. The next generation is completely decentralized, so therefore you do not need anything. You just start your application, they connect with each other in a very robust manner, and then they can start communicating. And runs on macOS, Linux, Windows, and we also are intending to port it to QNX and to VxWorks and all the other real-time operating systems. And I think this is not a challenge, because the biggest challenge of porting Iceoryx was to Windows, which is really something. Currently, we have also language bindings for C and C++. And thanks to the community, we never realized, for instance, that Iceoryx is a big deal in the high-frequency trading industry because of its incredible latency. And they offered, OK, we need Go, for instance, in this area. And then they are providing now us Go binding. So therefore, a big thank you to the community there. And also, currently, we are focusing on Python. And then the next thing will be also Java, Kotlin, SIG, and so on. But in the end, let's go a step back and take a look what inter-process communication in itself actually is. Let's assume this very simplistic use case. You're sitting on a Friday afternoon on your laptop listening to music, and now the next song comes, and the music player says, hey, now I'm playing song X. You get notified via a little notification daemon and say, hey, I'm now playing song X, and you say, this is not my favorite song. Skip the song, go to the next one, and then the media player skips the song and goes to the next one. What happens behind the scene is inter-process communication. So when you take a look, we have your music player, and underneath the music player, you have an IPC layer, which is tightly above the operating system, and this establishes communication between, let's say, for instance, a notification daemon to tell you, hey, the next song is playing, or hey, I'm a mail client, for instance, you have mail. And then again, with another process, for instance, like with your window manager with Windows, you have these media keys. You just send a notification to the media player and say, hey, next song, please. And then again, you send a message to the media player to play the next song. This is a typical IPC use case. So in the end, you have multiple areas where you use inter-process communication. One big, let's say, use case is you have a desktop system. You have written your UI, for instance, with C++. But your community want to extend your UI, your product with Python, with Perl, with Lua, with SIG, with Java, you name it in the end. And you want to all support this. So therefore, the idea is you stick with your language, but you define some inter-process interfaces so that they can connect to your product and then can send commands there and extend your product. Another thing is AI. AI is the use case. You have your one app, and you want to put this data into your large language model, for instance, so that it can operate on this and provide you some suggestions. Therefore, you sometimes get a big load of data into your model, and then it transforms it, comes up with a suggestion, and puts it back to your application. Another thing is microservices. This is also, let's say, a typical architecture we find in e-commerce, also with Go in mind, with the language. We have a lot of tiny microservices let's say, spread it all over the systems, maybe on one PC or on one computer, or maybe it's distributed over multiple servers. And here you also need IPC to connect them so that they can exchange messages. And one of the, let's say, biggest use cases we have shared with automotive and desktop system is robustness. Chromium, for instance, the web browser does it. For instance, every tab is running its own process, meaning when you visit a website and for whatever reason it causes a crash in your web browser, just this tab crashes, not your whole web browser, so that you can continue browsing and just, let's say, close the tab and continue. And the same thing we have for automotive. This is an extremely simplistic automotive use case. Assume you have a car and has a front radar and a back radar and a left and a right camera and so on. And here, you start maybe with a monolithic application. Everything is in one process. They all work happy together in the end. But now some kind of user guy comes and says, OK, in a safety-critical scenario, when your, for instance, right camera crashes, the whole system must still run stable. It must go in a safe state, but you cannot crash the whole car. It's a very bad thing when you are on a highway with 120 kph. So therefore, when you have a monolith, the right camera crashes, the whole system crashes, and you have to somehow mitigate this. So the idea is distribute the system. Extremely easy. And these blue lines are then the connections, which are inter-process communication, for instance, and then they are all happily communicating with each other, for instance, and when now the right camera goes down, then only the right camera goes down, the system remains stable, and you can continue operation, maybe in a fail-safe mode, but in the end, this is a typical IPC use case. So now let's assume, say, OK, yeah, it all makes sense. Now I apply this to my, let's say, automotive use case, and then you come up to me and say, OK, before we go there, first of all, I want to just capture the insights we have gained here. The first thing is that inter-process communication is really everywhere and has a broad use case spectrum, and the other thing is that it's a crucial part for a robust system. You have to somehow split the system from a monolith to a distributed system, so therefore that when one part of the system breaks, not the whole system is affected, and for this you need inter-process communication, or let's say some kind of communication. So now we have applied this suggestion and created a distributed system, and now we're running in this issue. With your monolithic system, it was fine, the CPU load was fine, the memory consumption was fine, and now you have a distributed system, the CPU load skyrockets, and the memory usage is massive. What's happening there in the end? So therefore, you have now an unusable system. It's robust, but unusable. What's happening behind the scenes? So let's take a look at a very simplistic example. You have one sender which produces 100 megabytes of data and wants to send the data to 3 receivers. So in the first step, the sender produces the data. Maybe it's a big camera image or whatever. And this costs you a little bit of CPU load and a little bit of memory. So therefore, we have now a memory consumption of 100 megabytes. But before we can send it, we need to serialize the data. This costs you, again, a little bit of CPU load and requires additional 100 megabytes of data, roughly. Here are serialization protocols like Captain Proto and Flatbuff and so on, which have optimized these steps. So therefore, you have either a zero-copy serialization format, or let's see, at least a zero-copy or zero-overhead deserialization format. But just for fun, like with DDS and other serialization formats, you have this require this step. So now you have serialized your data, and now you copy the data to all of the receivers. They receive now serialized data, and now you have a total of 500 megabytes in the system, and it causes a lot of CPU load since you have to copy it all over to every receiver individually. So the next thing is now the receiver would like to consume the data. So therefore, it has to, again, deserialize the data, do that again, the original data. It costs you, again, memory. Now we are at 800 megabytes of memory, and we keep also the memory on the sender side just to make sure that when a new receiver comes up and says, I'm also interested in data, can you please deliver this to me? You have to just be able to, let's say, deliver it quickly. So therefore, you have to keep it there. And now we have 800 megabytes, and now we are ready to consume the data, so therefore we can remove the serialized data on the receiver side, consume the large data, and now we have a system with a peak memory usage of 800 megabytes, but in the end, the payload was just 100 megabytes in the end, just because we are here pursuing like a network protocol approach, but we are inside one PC, one ECU, for instance. We do not need to serialize here. So the question is, can we get rid completely of serialization and deserialization? The other thing is, can we reduce the memory usage? And can we also reduce the CPU load? And here, this is the motivation for zero-copy communication. If you have a system and experience exactly this, you have it distributed, and then the CPU load skyrockets, the memory skyrockets, then you need something like Iceoryx, zero-copy communication library. So what we do here is the same thing. We have a sender. It produces data, 100 megabytes, but instead of producing it locally, it puts it directly into shared memory. So therefore, now we have our 100 megabytes of data stored in shared memory. And in the next step, we just set a pointer to the data in shared memory. So instead of having 400 megabytes or 500 megabytes of memory in use, we have now 100 megabytes and 24 bytes in use for the pointer. And when now the receiver wants to consume the data, it just dereferences the pointer, takes a look at the correct shared memory position, says, OK, here's my data, now I can read it. And here, it remains that the memory usage and the CPU load is not really affected by the communication at all. And this is something where you have the need for zero-copy communication. If you have a distributed system, you are in one ECU or one PC alone, and you're applying a network protocol to this problem, you will run into exactly this problem. And this is where Iceoryx2 shines. And this is where we have written Iceoryx2. So the insight is, now additionally to that we require inter-process communication for a robust system, that we also require zero-copy communication as an essential part for a non-trivial inter-process communication system. So the next section is why Rust. But I wanted to start is why you should not implement your own zero-copy shared memory implementation. In the past, we had a lot of customers which did this, not successfully. And also, when you take a look out there in the open source about communication library, you find a ton of, let's say, for instance, DDS implementation. You have Cyclone DDF, you have Fast DDF, you have Rust DDS, Dust DDS. There are countless network communication protocols, also for MQTT and so on. But when you take a look for zero-copy communication, you just find Iceoryx. And there's a reason behind this. You have multiple challenges we have to master. The first thing is security. The main problem which, again, arises is, in the first place, we split up the system to become more robust. But now, again, we're connecting services, or let's say processes, with shared memory. So therefore, again, they share a shared memory region. In this memory region, a rogue process, for instance, can corrupt the memory. When the memory is corrupted and then the data structure contained in there is invalid, you may be segfaulting. So therefore, the beauty we had reached with our distributed system is now broken again due to shared memory communication. We have to repair this. And these are all the security issues. We have to take care that a rogue process cannot modify the data of a receiver or a sender, or can send data in the name of another process, for instance. Or the other thing is, for instance, that a sender publishes data, the other one consumes it, does a check, for instance, are they valid? Yes, the data is valid, and now the rogue sender goes, yeah, now I changed the data in shared memory, haha. This is something we have to avoid. The other thing is safety problems. Here the key thing is a process can crash at any time. So therefore now you have this beautiful shared memory architecture, and now in the middle of communication, the sender or the receiver dies. How do you regain your resources? Do you now have a leak in the system? Or maybe have corrupted the data structure because you had a blocking algorithm, and therefore you safeguarded it with a mutex. Now you crash, and now you have a corrupted state, and you cannot recover from it. This you have to address. And also, by accident, it can happen that you have a sender sends out data, and later, after it has sent the data, because it's in shared memory and he has right to access to it, he can modify the data afterwards and then uses a data race in the other process. To mitigate these things, we require, for instance, concurrent resource management, meaning that when a process or a whole system comes up, they create resources. This has to be mitigated, or I'd say handled in a concurrent, safe way. And also, you have to pay attention that any process can crash at any given time. So therefore, you have to be prepared for it, and you have to mitigate this. The other thing are log-free algorithms. These are the keys behind Iceoryx, the communication infrastructure. In the end, when you take a look at a communication framework, you always have some kind of a queue where you just put in the data, and then on the other side, you put the data out. Since we are not allowed to use blocking algorithms because you could crash at any given time, we are using log-free algorithms. But log-free algorithms are extremely nasty. Our central algorithm took us roughly a year at Bosch to implement. We had multiple sessions with really the best developers we could find there at Bosch. We were part of this. We were very proud about this. But then after 3 or 4 years, and when we started playing around with Rust, we found a bug. And this is something which you do not want to have in a car. This should be really safe. And here, also, this is something where Rust shines in detecting concurrency issues. I will come later to this and provide an example for this. The other thing is, because we have shared memory and we have not just bytes in there, we have data structures, allocators in there, they have to be incorruptible, meaning when one process tries on intention corrupting this data structure, we at least have to detect this and can say, okay, this guy is a rogue process, I do not want to connect with them anymore, and I now disconnect to him, for instance. Or you just mentioned or send some signal to a watchdog, for instance. And also, it can happen, these nodes can crash, you have to also clean up their mess, their resources, so that they can continue operation. And all these challenges you have to master to have a reliable zero-copy communication for a desktop system, and not for a car. And for a car, you have the additional challenges of safety certifying this, and also to provide a formal verification for a log-free algorithm, for instance. So therefore, it piles up. So, but we face the challenge, and we are very confident that we have mastered them now. So in the end, the major challenge we have mastered is a process can crash at any time, so therefore we are not allowed to have blocking algorithms. Bugs in a process can corrupt any part of the shared memory, therefore we have to safeguard the shared memory so that you do not by accident modify something which is read by someone else. And a rogue process can corrupt the whole system, and we have to also prevent this. How does Rust help us here? The best thing we can do here is just do a side-by-side comparison with C++. We can do this very well here, because the first iteration of Iceoryx was written in C++. We also went through safety certification for ASLD with Iceoryx, with the Whos library there. And also now with Rust, we now know all the advantages firsthand, which we saw during the development of Iceoryx2. But just imagine you are a developer and you're reviewing a pull request which just changed this colored one line, this update connections. It's fully tested. He has written additional tests for this. It's documented what it does. We have an issue for this. The issue was sometimes you send data to receivers which are no longer there. Well, therefore, update the connections to check if the receiver is still there, and if not, you just update the receiver vector and continue operation. And also the CI pipeline passes, the test passes, and so on. But sometimes they don't. The question is, what's happening here? So in the end, what you see here in the slide is you have a vector of receivers. You iterate over the receivers for every receiver. You just deliver the data pointer like we have saw in the example, for instance. Then you call update connections, and it sometimes crashes. What's wrong here? Let's take a look here. What happens behind the scenes is, which I now stated to you, is it removes receivers or adds newly collected receivers. So therefore, it seems to modify the receiver's vector, something which you do not see in your pull request. You just saw in your pull request this added line. You have no idea that in a different file, there's a different function, update connections, and it's an internal function, so therefore it's maybe not as well documented as a public API that it modifies the receivers. You just know, okay, I have to call update connections to reconnect receivers. And the thing is, when you take a look at the C++ standard, you'll see that as soon as you modify a vector and you continue iterating over it, all the iterators are invalidated and you have undefined behavior. Now we run into undefined behavior land, and you crash sometimes because undefined behavior is evil, because it sometimes shows and sometimes it does not show. I mean, you think now it's a constructed example. We have 2 counterexamples. It happened on our side during the development of Iceoryx1, and it also happened to Firefox, so therefore we are not alone. But let's take a look at how Rust would handle the same thing. If, again, our receivers, we iterate over our receiver's vector, we deliver the data, and then we want to call update connections. And then the Rust compiler says, oh, no, you cannot do this, because Rust has strict borrowing rules. You can either have one mutable reference or arbitrary many immutable reference. You cannot have a mutable reference and an immutable reference at the same time. What's happening here behind the scenes, and here the developer was not aware of this, and this can happen extremely easy because you as a developer are overwhelmed with all the information. So let's say you have to be aware of C++ perfectly, of all the internal implementations perfectly, and therefore it's just slipped that here we have 2 mutable borrows. First of all, when we iterate over the receivers, we get immutable borrow from the receiver to deliver data, and then when we call update connection, we again modify receivers with immutable borrow, which is illegal, and therefore compiler does not compile, and therefore you have not to review this pull request. So this one rule in Rust, that you have either one mutable borrow or an arbitrary many immutable borrowers, prevents you actively from undefined behavior, as we saw here with C++. It prevents data races. This means, for instance, the following. Let's assume you have a multi-threaded system, and you have here one guy modifying the data while another one is reading the data. You violate the borrowing rule, and therefore you have a classical data race. Can happen all the time in C++, but with Rust, such a code does not compile. And now the final point here is it takes away the cognitive load of a programmer. There are a lot of arguments out there to say, okay, you have to be aware, you have to know what you're doing it not carefully enough, and so on. But here I want to provide you an analogy. The best chess players can think 8 moves in advance. A chess game is very simplistic compared to a software of a car. You have here 64 fields, you have some pieces, and so on, and they can only think 8 moves in front of, say, for each move. So with this, the developer has to be perfectly clear about all this C++ specification, which is a lot, there's multiple thousands of pages. Then it has to be aware of all the details, implementation details of the software, and it also has to be aware of, let's say, the safety manual, which Unix delivers you, or let's say other vendors deliver you. This all has to be stick in your head. You have to be aware of this when you're reviewing the pull request. I think it's clear that this is insane and does not work. So therefore, you need some kind of mechanisms to handle this. And here is something where Rust shines. Here you can explicitly in the API describe the contracts in the end. And this is something which with C++, for instance, you try to strive for a good API which cannot be misused, which is can be easily read, where you have a clear documentation, but you can always by accident misuse it easily. With Rust, you can actually, when you just stick to safe, not to unsafe Rust, create an API which cannot be misused. And just think about the time you have to invest to just find such a bug. These are weeks. And I speak here from experience. So another example is, assume you have an automotive use case and you have an image which you get, and you want to calculate the acceleration of all the objects in this image. Well, therefore, you do not need one image, you need 3 images to calculate the acceleration of all these objects. Therefore, the idea is, okay, we just create a cache. In the first line, it's just a vector of samples. Then we create our receiver. Then we call data equals receiver receive to get our data and just store it in the cache. And that's all there is. This is our simplistic program. And it sometimes crashes. Why? What's happening here? And this is, in the end, maybe behind the scenes written in some kind of documentation where there was a little note that sample has to live longer, the receiver has to live longer than sample. You as a developer has to be aware of this. It's also in the safety manual noted, but in the end, because you have to remember, let's say, 10,000 pages of manuals and so on, you maybe slip this little teeny tiny detail. And when you do the same thing with Rust, you now experience the following. You create your cache, you create your receiver, and now you try to store the data in the cache, and then you get, oh, okay, receiver does not live long enough. Because we can really define in the API and can say, okay, we have a lifetime contract. The receiver must live longer than the sample. And this is verified by the compiler. And again, these are bugs, not, let's say, constructed bugs. I can give you GitHub issue links where we have managed these bugs, and it took us months to sometimes fix them. And this is something where Rust shines in the end. In the beginning, it has a steep learning curve, but if you have at some point mastered it, you can really focus on your algorithm. And here, by the way, the fix for this is just revert the lines. If you revert the lines, the destruction order is reverted, and therefore everything is fine. And this is something with C++. To find this with C++, good luck. And static code analysis and so on may be not helpful here. The address sanitizer sometimes finds such a thing, but not always. So again, the compiler verifies lifetimes. It helps you to, again, to prevent undefined behavior, which is the worst thing that you want to have in a car. Undefined behavior, meaning you have no idea what the car behaves, and undefined behavior means really undefined behavior. Or like Herb Sutter mentioned it, it's like pink elephants. Everything can happen. and also dangling references, which are the underlying cause of some undefined behaviors. And again, it reduces the cognitive load of the developer, because maybe you have read the manual, maybe you understood it, but it was a harsh day, you are now in the 9th hour of your working day, you drink your 6th coffee and so on, time is pressing, and you say, okay, I have to get this feature in. And you just forget this teeny tiny detail, the CI pipeline is green, everything works, but then, as you have heard in the previous talk, is you deploy it to the car and suddenly it crashes in the field because you missed this teeny tiny thing. So the other thing is, an additional insight is that Rust's lifetime borrowing checking really actually prevents bugs and makes your development faster. And the other thing is, don't implement zero copy on your own. If you try this and you master this, please contact us. I would like to know how do you do that. But in the end, it cost us 7 years to really master this, and we are still encountering bugs and try to improve concepts continuously. It's an ongoing challenge. It's like cryptographic algorithms. You also should not implement cryptographic algorithms on your own. So why you should use Rust? Iceoryx, and also Rust. But here, the 5 insights, but also, let's say, Iceoryx is intended for mission-critical systems. So therefore, right from the beginning, we have written this so that it is certifiable according to ISO 26262. Also, I think when I looked about the different network communication protocols and also shared memory implementation is maybe the fastest IPC library out there. I would have shown you proof on my laptop, but for technical reasons, I'm now out of the loop. So it's written in a memory-safe language, Rust, and it runs everywhere in the end. Currently, it runs on Windows, Linux, Mac OS, FreeBSD, and soon Android will follow, and also, let's say, the RTOSes. Iceoryx1 is already working on FreeRTOS and QNX, so therefore there should be no obstacle to all support Iceoryx2. The other thing is, it's an open source project, and what we saw in the past was that we had a lot of users, and they wanted help, but help something which we could not provide because we really needed contracts for it, and we hadn't the time, for instance, to focus on other customers. Let's say having a specific Eclipse Iceoryx issue for high-frequency trader when you are at Daimler, for instance, or at Bosch, and you are focusing on a customer from automotive world. Then you do not have time to focus on a high-frequency trader from Singapore, for instance. But now with this company, we are able to do this. And also what yesterday we showed to the world is we have now also an RMW Iceoryx2 layer for Rust 2. For Iceoryx1 it was already there, and now we have also the ability in the end, since it is focusing for mission critical systems, to have a smooth migration path from Rust 2 to Iceoryx2 standalone, keep communicating with each other, and have a, let's see, a CRFD certified system. And also something which is interesting for the community, at least, and we found it out, is that out of the box, Iceoryx comes with safety critical building blocks, meaning we have a std vector, for instance, a std string. We required this on our own to safety certify our software. There we just created the artifacts, but as it turns out, everyone needs an STL implementation. So therefore, why not use this one, for instance? And the same thing goes also for Rust. When Ferrocene, for instance, they certify the compiler, they make the same thing like with C++. You cannot certify the STL or the STD in Rust terms, and this is also something we require. We require it to be safety certified, so therefore we provide this as open source building blocks, which you can also use if you do not have an IPC use case. So, and this is the latency I was speaking of, and this is something we are talking here about nanoseconds, and in the previous talk from Sino, they showed, let's say, how fast they are. They have, let's think, the best case was 7 microseconds or 7,000 nanoseconds, which is impressive for a network protocol. But we are not a network protocol, so therefore we do not have to take care of serialization of all these syscalls we have to call. We can have a shared memory, we can have atomic operations in there, and we are incredibly much more faster than, let's say, a network protocol implementation. Like around 70 times faster. My laptop, I tested it on my hotel room, is around 150 nanoseconds in battery mode during an open presentation, and I can show it later if you want. And we have also a grand vision with Iceoryx, which somehow overlaps with U protocol. Here the idea is because we are so low, we are directly above the operating system, we already have a great community which provides us with gateways and with language bindings, and okay, we have already here ROS2 and RMW Iceoryx2, which it's currently open source, but it's not really yet usable, it's in a beta state. Also, we had with Iceoryx1 an adaptive autosar state where we have just provided how you can put a proxy and skeleton above this implementation. We have our native Iceoryx2 apps, which are already working, and then we, for instance, want to have also our customers at least want this network communication. You want to use one Iceoryx instance on one PC and then communicate with another Iceoryx instance there. We are not experts in network communication, but the Sino guys, for instance, are. So therefore, we just build a Sino gateway and have then communication to other, let's say, Iceoryx instances, but also to Sino applications. And also there are other cool DDS implementations in the Rust universe, Rust DDS, Dust DDS, for instance. You just create gateways there. Or RumQTT, it's a MQTT implementation in Rust. And then we can create all these gateways together. And because Iceoryx is the lowest building block, it's the lowest communication layer you can have on a PC, then you can use it directly for connecting everything in the end. And this is something which we already have done in the past, for instance, with Cyclone DDS. Cyclone DDS uses Iceoryx as a communication layer if Cyclone DDS knows that the other participant is on the same PC, for instance. And also, what we are working on is, in the end, that we want to have Android support, Conix, VxWorks, and also, since we are handling with shared memory, and another, let's say, automotive use case is with NVIDIA incorporation. You have a camera, you publish a lot of camera data, but instead of publishing it to the normal memory, you just publish it directly to GPU memory. And now you want to, let's say, handle the data directly on GPU, do your filters, detection, and so on. But here the thing is, when you do the communication, you do not want to go over the CPU, tell the other process, hey, I have data for you, and they go again to the GPU, copy it, and so on. You want to have this bottleneck as tight as possible. And therefore, you want to, let's say, trigger directly from one GPU process to the next one GPU process, and Iceoryx should just provide here the abstraction. And in the end, this is our same grand vision as with View protocol. You as a user don't care. You just say, send data. I don't care. If it's using Sino, DDS, whatever, I don't care. Just get it there, and the other interested party says, okay, I want to have, let's say, I'm a subscriber or a server or a client, and I just want to receive this data. This is our long-term vision, but here I want to point something else. You always need a long-term vision where you want to converge to, but it does not mean that Iceoryx has to do all the stuff. You guys can do also something. Well, therefore, I'm extremely happy to collaborate here. I want to point this out. But in the end, it's nice that we at least have the same vision, and then we can continue to do great things together. And with this, I want to conclude my presentation. And a final note I wanted to state, we announced Iceoryx2 at the end of last year, and since then I have no idea what we did, but we have grown some kind of community, and they are now happily providing us with Go language bindings or with gateways or with a command line client and so on. And therefore, I want to just say thank you for this. And now I'm open for questions.
Okay, so first, I want to say thank you, because I love when more and more communication protocols come and present at these functions, because it shows the need for uProtocol. But having said that, the idea is that we need to have, Iceoryx is great for a specific use case. It could be used for many other use cases, but you need to really pick a collection of protocols in order to build a service mesh. Anyway, but the question I had is, with this new Rust core implementation that you have, do the other language bindings bind to the core Rust, and the core Rust is common? So if I want to have a C++ client, I will have a C++ language binding API, and then it will just call down to...
Exactly.
Cool.
Yeah.
Thank you.
One question from my side concerning Rust. So how intensive is the rewriting of code if we want to switch from a C++ code to Rust?
I think that the first step is a little bit overwhelming, because you as a C++ developer, or let's see, I talk about me. I had the arrogance that, yeah, I know what I'm doing, and yeah, compiler don't tell me that I'm wrong here. And then after, let's say, sitting down and relaxing a bit and say, okay, this damn thing is right. And here this happens to you over and over again. And it's like with every new language, you have different idioms and so on, so therefore it takes you some time. But here the thing is also this is something where Iceoryx can help you, and this is a very particular use case we have. Let's assume you have an old legacy code base, C and C++. A good way, for instance, to start to learning Rust is write some command line tool. You need always some kind of command line tool to handle something, to manage something, and so on. You start with this. And then you go deeper into the project and say, okay, now if this part of the code base in C++, let's try to rewrite this in Rust. And this is exactly where Iceoryx can help you. You just have then an IPC connection between these two. You keep your legacy code like it is, and you just add new Rust functionality to it. And in the end, it should be as easy as a function call. So
the design will still as it is, no differences in the code architecture?
No, when you now take a look, let's say, at Iceoryx itself, there's a huge difference in the architecture. When this was a question, okay, sorry, I missed it. Here the idea is when we looked at Iceoryx1 and said, okay, we want to safety certified, and then we saw a lot of weak points we have because we are still learning, and then the challenges I presented there, then they occurred as, okay, we have here another challenge, here another challenge. We have to refactor the whole code. And then at this point, we already started a little bit of Rust playing that, let's try it out in Rust. Let's see how well it is. Everyone says it's a great language. Let's really see if it proves right or wrong. And we started with this, and then we also found a lot of new amazing things, meaning with C++, we encountered still at this really mature state, segmentation faults, some kind of concurrency issues, and so on. And we had all the safe checks in place. We had address sanitizers, we had thread sanitizers in place. We had in some part here, how's it called? Testing framework to test concurrency issues and log-free programming, let's say memory synchronization issues, and they all could not find the issues Rust easily found. And this was so much time we invested in this particular scenario, months. And with Rust, it's just, it does not compile here, by the way. This is, and they just take a look and say, okay, you're right. And here, for instance, we have also a list of issues we just found because we re-implemented this in Rust. And we re-implemented, let's say, a log-free algorithm for a queue in Rust, and then the compiler said, no, it does not work. Or Miri said it, and then we said, okay, you are right, we would never have found this. Then you saw it, and it was obvious. So
maybe in the beginning it's difficult, but later it's easier to...
Exactly. What you, for instance, when you are a startup, when you want to create a quick proof of concept, C++ is faster. But then you have a proof of concept which is somehow together put with stick and a little bit of chewing gum and so on, and you hope that it stands when you put up the next feature and the next feature and the next feature and so on. And at some point it breaks, and it also breaks your neck because then you have to do a refactoring for multiple months or years maybe. With Rust, you have a steep learning curve, but you make steady progress. So therefore, the proof of concept, you're faster with C++. But right after this, it soon comes a phase where you can just deliver features continuously, reliably, and the C++ guys have increasing technical depth, have to fix bug fixes, which are extremely hard to find and really demotivating. And I was there. I experienced both sides now, and I'm happy with Rust. I'm just a more happier developer, so therefore.
Thank you very much for your presentation.
Thank you.
Yeah, my question goes, so to speak, in the same direction. Did you, for your core algorithm, like the log-free stuff, look into some more formal methods like TLA plus and route it in there and run it? Because I think that can find even more non-trivial bugs than Rust. Rust is a great start.
Yeah, you're completely right, and we have to go this route. So therefore, what we have to do is, when you take a look at the MISRA standard or AutoSAR and so on, the coding rules, when it comes to log-free algorithms, you find nothing there. Except don't produce data races, thank you. Sorry, it's like going to the doctor and he says, yeah, you have to become, do not be sick, thank you, okay. And here the thing is, yes, we looked into this. TLL plus is something which we found not so useful. We want to more go for Spin. Spin is a framework they used also for the space shuttle to formally verify their code, so therefore this is an approach. And we want to combine is also explore Kani. This is also a formal verifier for Rust. We're a little bit cautious there because we hear it, but this is something I'm not an expert in Kani, just that it has to also, let's say, implement the memory model there, and this is a huge undertaking. Let's find out. I have no idea.
I just have a stupid question for Rust. One of the problems with C and C++ for formal methods is the preprocessor, because the preprocessor doesn't follow any of the syntax of the language. What are macros like in Rust?
Okay, good question. In the end, what you have macro hygiene there. So therefore, even though that you have macro and you have also preprocessor macros, they follow a strict syntax. You cannot do anything. It also poses some kind of challenges. For instance, because you can do anything, it's really easy in C++ to implement, or really easy, branch coverage, MCDC coverage. We can utilize here if and override it with a macro and say, okay, whenever you call if, for instance, you do this. Or become extremely evil for a C++ developer, just say define true, false, and see how long it takes for them to fix the bug. And this you cannot do with Rust.
Yeah.
You have here the macro hygiene, you have a certain macro syntax which prevents you to do such crazy stuff.
Yeah, that should help actually writing formal tools, because then you don't have this semantic or syntactical dissonance between macros and the rest of the code.
Exactly.
One
Hi.
last short question.
Okay. Sure. So I have one question. You mentioned that in Iceoryx2, you have this decentralized concept now, and no more central program, RouDi, whatever the name was in Iceoryx1. And what about this memory management? So is it still needed to pre-allocate memory clusters that then be used by the system, or are you flexible here if a new publisher started at runtime and creates some message?
Yeah. Nearly perfectly dynamic. Currently, what you have to do at runtime, not at compile time, is you have to tell the publisher, hey, I want to send this data, and it can become dynamic, but you have to give a worst case size. And say, okay, it will not be more than 1 megabyte, for instance, for a sample. But this is still a restriction we do not like, so therefore, in the next step, we will go in this route that you just say, create a publisher, it has dynamic data, I have no idea how large it is, figure it out on your own. Here, the thing is, if you go this route for a desktop system, it may be a viable approach, but then you have to, under the hood, reallocate, because you have maybe out of memory. Desktop system, no problem. Real-time operating system, you are reallocating 10 gigabytes of memory. This will be a huge jitter in your real-time operating system, so therefore, you have pre-allocated memory. This is our static approach, and if you're going to a desktop system where you don't care, gloves off, do what you want.
So a follow-up question, how does Rust deal with fragmentation? I mean, if you dynamically allocate and deallocate, then the typical problem there is fragmentation.
Yeah, here the thing is, the first thing is, in automotive use case, we are trying not to use heap, because under the heap you have something like a body allocator, the algorithm itself has defragmentation problem, or it's defragmentation problems. We have to avoid this, so therefore the underlying algorithms or allocation algorithms we have in Iceoryx are pool allocators, for instance. Here we have very specific sites, it does not change, for instance, and we have also for desktop systems the ability to create an extension of a body allocator. Then you have to deal with all the fragmentation problems, but this is then on your own. You have the freedom to do this, but by default, you have to define this, let's say, worst-case memory size, and then you get exactly your piece of memory, which is pre-allocated. You do not have fragmentation, and you have the guarantee that you never run out of memory as soon as the publisher was created. Okay.
Okay.
Very good.
Thank you. Time's up, more or less. Thank you.